Good morning. Over the next couple of short videos, I'm going to attempt to provide some solutions or some hints on a few problems from the optimization unit section 4.7. Number 23 is the first one I want to look at, so let's get right into that. In number 23, we're given a triangle that's formed by the point that goes through the point 1, 2, but it intersects the x and y axis at two points. And of course, those points could be x0 and 0y. Well, this will eventually be a calculator problem where you will need to type the function into the calculator and find the max or min, whatever is required. The first part was to write the length of this altitude, or the hypotenuse, I should say, in terms of just x instead of x and y. Well, first of all, it's pretty easy to see that the length from this point, x0 and 0y, I'll call it L, is simply the square root of x squared plus y squared. Simple Pythagorean theorem, distance formula, whatever you want to call it. So now my goal is to somehow write x in terms of y. And this is where kind of the trick is. That's our main function. We only want one independent variable. Well, one thing I notice is that the slopes of these two little sections must be equal. So in other words, the slope of this little section, let me get a different color here, because I like to. The slope of this one section is just the difference of the y's, which is 2 minus 0, or 2, and the difference of the x's, which would be 1 minus x. That's the slope of this section. The slope of this other section is going to be the difference of the y's, which is y minus 2, and the difference of the x's, negative 1. And so now your job is to solve for y. Well, I've done that for you, but you can check it. Y will eventually be 2 over x minus 1 plus 2. So that would be an expression for y. We can definitely play with that a little bit. We can get it into one big term. It doesn't really matter. So now what I have is a length formula, the square root of x squared plus all of that squared. And again, some algebra may be helpful before you would type this whole thing into the calculator. So for part A, that's the length in terms of x without being very simplified. For part B, we then want to minimize the length. Right? So in order to minimize the length, we now just have to find the derivative set it equal to 0. And again, this is a calculator problem. We could find the derivative analytically, but there are some of these that are a little bit beyond what we want to spend time on. And so we find the derivative simply by graphing this function and find the max or min. For part C, we want to minimize the area. Well, again, we start with an area formula, which we know is 1/2 base times height. But the base of this triangle is x, the height is y. So before you know it, you end up with the area to be 1/2 the base, which again is x, times the height, and the height is that y value, which would come back to this. 2 over x minus 1 plus 2. Once we have that area formula, same thing. We can find the derivative, set it equal to 0, find the x value that makes the area the smallest we can get. So that's kind of a recap of 23. I would go through some of the details and make sure it all works out for you. The second one I want to look at is number 27. Sorry, number 25. So let me put that up here. In this situation, again, it's one of the most classic type of max and min problems we have. We have a semicircle, And then underneath the semicircle, what we're going to do is put a rectangle. We want to build the biggest rectangle we can. So we do eventually want to maximize the area. Yes. Well, if we take a look at the equation of this circle, or semicircle, we are given that it's going to be the square root of 25 minus x squared, meaning that this is 5, this is negative 5, this, of course, is 5. So that's a semicircle. It's the top part of the circle. What we have for the rest of it is this is some value x. We don't know it. But if we want to maximize area, that's always going to be our first step if we can identify it. We then write an area formula. Well, in general, the area of any rectangle is simply just base times height. Now we have to turn it into a formula that only has one independent variable. We can see that the base of this rectangle from here to here would end up being 2x. The height of the rectangle is basically the y value, but the y is the same thing as radical 25 minus x squared. So what we end up with is a function that we can now differentiate. Set it equal to 0, find the x value that's going to give us the biggest possible value. Squeezing one more problem in this short video. Number 27. 27 is about a package, and we want to maximize the volume. Well, the volume of this package, since it's a box, is simply going to be length times width times height. Well, if you look in the text, you will see that the length of this package is y, the width and height are both x. Because what we basically have is a box whose cross-section is kind of a square. And what we have after that, and I could play with this a lot, okay, that's y. Maybe you can see a box out of this, I don't know, but the book would have a better picture. So what we have is the cross-section being a square and the length being the span or y. So that's going to be our volume. Well, in order to get rid of one of those variables, we are given something about this thing called girth. And girth is nothing more than the sum of the cross-section, perimeter, times its height. So basically the girth would be 4x plus y. And we are told that that can't be any bigger than 108. So I'll just make it 108. And this is where we end up with a secondary equation. That secondary equation allows me to create a function with only one independent variable. So we have 108 minus 4x. That's the length. The width and height are still both x, so I'll make that x squared. Then there we are again. Find the derivative, set it equal to 0. Very simple derivative. So it's a little bit more complicated. Very complicated, so we're going to use our calculator. So these are some solutions, or at least kind of scaffolding of what the solution could look like for 23, 25, and 27 from section 4.8. I'll be right back with the second video with 2 other solutions.